Early 1962. Gary, Indiana. The blast furnace heat shimmered across the long-span rebar works as molten steel poured into casting molds, sending sparks cascading across the factory floor. Superintendent Jack Reynolds watched his crew roll glowing steel billets through the finishing stands, each deformed bar cooling slowly on the 45-foot run-out bed. The entire steel industry had already decided. Rebar was cheap commodity steel. Use scrap metal. Cut corners. Roll it fast and ship it faster. European mini-mills were proving that quick quench methods and recycled materials could meet basic building codes at half the cost. But Reynolds was running his operation like it was still 1940, virgin iron ore, strict chemistry controls, old-fashioned air cooling that took nearly an hour per batch. His competitors called it wasteful, his bosses called it expensive. What none of them realized was that Reynolds was building rebar that would still be holding up bridges 50 years later, while today's cheap rods were already starting to fail. The interstate highway system was devouring steel at an unprecedented rate. Across America in 1962, construction crews were pouring concrete for bridges that would span rivers from coast to coast, erecting buildings that would define city skylines for generations, and laying the foundation for infrastructure projects that would carry the weight of American commerce for decades to come. Every mile of highway, every bridge pier, every high-rise column demanded thousands of tons of reinforcing steel, rebar, to give concrete its backbone. The established players in American steel had already reached their verdict on this market. Rebar was commodity steel, pure and simple, low margin, low grade, and getting lower every year. The integrated mills that had dominated American steelmaking since the 1890s were systematically exiting the reinforcing bar business, ceding the territory to a new generation of mini-mills that had discovered the economics of electric arc furnaces and scrap-based melting. These smaller operations could take mountains of discarded steel, old cars, demolished buildings, industrial waste, melt it down in electric furnaces, and roll out rebar at prices that made the traditional blast furnace to rolling mill process look hopelessly antiquated. By the early 1960s, the transformation was nearly complete. Mini-mills were capturing market share with ruthless efficiency, undercutting integrated mills by $30 to $40 per ton. Their formula was simple: feed scrap metal into electric arc furnaces, cast the molten steel into billets, heat those billets in reheat furnaces, and roll them through finishing stands as quickly as possible. Speed was everything. The faster you could move steel from scrap yard to construction site, the better your margins. But Jack Reynolds had spent 25 years in integrated steel plants, and he knew something the mini-mill operators didn't want to acknowledge: heavy infrastructure, the kind of bridges and dams and high-load columns that would carry American commerce for the next century, demanded more than basic specifications. It demanded steel that would resist corrosion for 75 years, maintain consistent yield strength under massive loads, and bond reliably with concrete cover through decades of freeze-thaw cycles and chemical exposure. The son of Polish immigrants who had worked the blast furnaces in Gary since the 1920s, Reynolds had learned steelmaking from men who treated chemistry control like a sacred discipline. His father had showed him logbooks from the 1930s, where every heat of steel was documented with carbon content measured to the 100th%, phosphorus and sulfur levels tracked like vital signs, and cooling rates recorded with the precision of a medical chart. Those old-timers knew that small variations in chemistry and microstructure could mean the difference between steel that lasted a lifetime and steel that failed within decades. Standing in his office overlooking the long-span rebar works, Reynolds could see the future of American infrastructure taking shape on his drawing boards. His plan defied everything the steel industry considered economically rational. Instead of maximizing scrap content like his competitors, he would limit scrap to carefully selected grades with copper content below 0.1%. Instead of rushing billets through the rolling mill at maximum speed, he would take time to heat them to exactly 1200 degrees Fahrenheit in the reheating furnace, ensuring uniform temperature distribution before they entered the rolling stands. The technical specifications he had developed read like a manifesto against the commodity steel philosophy. 7 by 7-inch billets cast from steel refined in basic oxygen converters, not electric arc furnaces. Rolling down to number 5 and number 6 deformed bars with precisely 12 ribs per foot, each rib measuring 4/100ths of an inch deep with 6/100ths inch spacing. Most critically, those finished bars would air-cool on the run-out bed for 45 minutes, allowing their microstructure to transform naturally into fine pearlite and ferrite, rather than the brittle martensite that resulted from rapid quenching. Reynolds kept detailed chemistry logs that would have impressed his father. Carbon content held between 4/10ths and 4 4/10ths%, manganese at 0.8%, phosphorus below 0.03%, sulfur below 0.02%. These weren't the loose tolerances of commodity steel. They were the precise specifications of steel designed to anchor American infrastructure for generations. The market responded to his premium approach with skeptical indifference. Procurement officers for major construction projects blanched at his pricing, nearly $500 per ton delivered, while mini-mill competitors were bidding jobs at $420 per ton. The engineering specifications he championed: 60,000 pounds per square inch yield strength with 8% elongation at fracture, diameter tolerances within 5/1000ths of an inch, impressed quality-conscious engineers, but failed to overcome the relentless pressure for cost reduction. Corporate executives from the parent steel company visited Gary with increasingly pointed questions about production efficiency and market competitiveness. They brought charts showing how electric arc furnace operations could produce rebar in hours rather than days, how scrap-based feeding eliminated the expense of iron ore mining and blast furnace operations, how quench-and-temper techniques could boost yield strength while reducing processing time. The logic was compelling, the economics undeniable. But Reynolds had seen what happened when steel quality became secondary to steel pricing. A bridge project in Ohio had recently suffered embarrassing delays when mini-mill rebar failed elongation tests, achieving only 4% elongation instead of the specified 8%. The contractor had been forced to reject entire shipments, creating costly delays and raising uncomfortable questions about long-term durability. Standing beside the cooling bed where his latest batch of bars lay cooling in the Indiana evening air, Reynolds opened his logbook and reviewed the day's production. The chemistry numbers looked exactly right: carbon at 4 4/10ths%, phosphorus at 2 5/10ths%, sulfur at 0.02%. The microstructure would be perfect: fine pearlite with ferrite islands, no brittle phases, no decarburized surface layers. He could roll these bars the way his father's generation had rolled steel, creating rebar that would still be holding up bridges when the quick-cooled, scrap-heavy bars from his competitors had long since corroded away. But the business was demanding a different approach: faster production, cheaper inputs, higher volumes. The conventional path promised immediate market success, but Reynolds suspected it would lead to infrastructure failure that America couldn't afford. The decision to proceed came in January 1963, when Reynolds convinced the board to commit to a full production run using his integrated mill specifications. The logistics alone represented a massive undertaking. 200,000 tons of virgin iron-derived steel would flow through the basic oxygen converters over the next 18 months, supplemented by 50,000 tons of carefully sorted scrap that met Reynolds's stringent requirements: copper content below 0.1%, no chloride-bearing mill turnings, no automotive scrap that might introduce unpredictable alloy contamination. The sourcing operation stretched across the Great Lakes region. Virgin iron ore arrived by rail from Minnesota's Mesabi Range, the same high-grade taconite pellets that had fed American blast furnaces since the 1880s. Each shipment came with detailed chemistry analysis showing iron content above 62%, silica levels that would produce clean steel, and phosphorus low enough to meet Reynolds's demanding specifications. The selected scrap came from industrial sources: structural steel from demolished buildings, railroad rails, heavy machinery components, materials with known chemistry and no exposure to automotive fluids or marine environments. Reynolds established quality control protocols that would have impressed metallurgists from the 1940s. Every heat of steel underwent spectroscopic analysis before casting, with carbon content targeted at 4 and 4/10%, manganese at 0.8%, phosphorus below 0.03%, and sulfur below 0.02%. The basic oxygen converters ran longer cycles than typical commodity steel production, allowing more complete removal of impurities and better control of final chemistry. The rolling operation began in earnest during the winter of 1963. Billets measuring 7 inches by 7 inches in cross-section moved from the casting area into reheating furnaces, where gas flames brought them to exactly 1,200 degrees Fahrenheit. Temperature uniformity was critical. Reynolds had installed additional thermocouples throughout the furnace to ensure no cold spots that might create inconsistent microstructure in the finished bars. From the reheating furnace, the glowing billets entered the continuous rolling mill, a precisely choreographed sequence of stands that gradually reduced cross-sectional area while maintaining temperature control. The number 7 finishing stand operated at 1,000 feet per minute, fast enough for efficient production but slow enough to maintain the deformation pattern Reynolds demanded. Each bar emerged with a final diameter of 3/4 inch, designated as number 6 rebar, with 12 ribs per foot running the length of the bar. The ribs measured exactly 0.04 of an inch deep, with 0.06 inch spacing, creating the mechanical bond with concrete that would anchor these bars in place for decades. The cooling process represented the heart of Reynolds's technical philosophy. Instead of quenching finished bars in water or oil to achieve rapid cooling, the long-span rebar works used an extended air cooling system. Bars rolled onto a run-out bed that stretched 45 feet, allowing ambient air at 70 degrees Fahrenheit to cool the steel gradually from 900 degrees to 150 degrees over 45 minutes. This controlled cooling rate ensured the formation of fine perlite and ferrite microstructure rather than the brittle martensite that resulted from rapid quenching. Maria Lopez, the shift forewoman who had worked the rolling mill for nearly 2 decades, understood the difference that cooling rate made in ways that transcended metallurgical theory. She could tell by the sound when bars were cooling properly, a subtle creaking as the steel contracted, different from the sharp pinging of rapidly quenched material. She watched for the color transition from cherry red to dull orange to gray. Timing that told her whether the microstructure was transforming correctly. Her crew learned to stack the finished bars only after they had reached handling temperature, ensuring no thermal shock that might create internal stresses. The first major shipment left Gary in March 1964. 30,000 tons of number 6 rebar loaded onto flatbed rail cars bound for a bridge project that would carry Interstate 71 across the Ohio River. The contract specifications called for concrete cover of 4 inches over the reinforcing bars, generous protection that would shield the steel from environmental exposure for decades. Construction crews would place these bars in the bridge's tower anchor reinforcement, the critical structural elements that would transfer highway loads deep into bedrock foundations. Quality assurance testing validated every aspect of Reynolds's technical approach. Dr. Alan Grayson, the consulting materials engineer who had been skeptical of the integrated mill economics, conducted systematic testing on random samples from the Ohio shipment. Tensile tests on 1,000 bars showed yield strength averaging 61,200 pounds per square inch, well above the 60,000 pound specification, with ultimate strength reaching 85,000 pounds per square inch. Elongation at fracture measured 9%, exceeding the 8% requirement with margin that indicated ductile rather than brittle failure characteristics. Bond testing revealed the mechanical advantage of Reynolds's precise rib geometry. Pull-out tests in 6-inch concrete cylinders averaged 1,350 pounds per square inch, demonstrating the grip strength that would prevent bars from slipping under load. The 12 ribs per foot, each cut to exactly 0.04 inch depth, created mechanical interlocking that distributed stresses evenly along the bar length. Corrosion resistance testing provided the most dramatic validation of the virgin iron approach. Salt spray exposure for 1,000 hours, equivalent to decades of marine environment exposure, showed no visible rust formation on the bar surfaces. The low sulfur and phosphorus content that Reynolds had insisted upon paid dividends in corrosion resistance, while the absence of copper contamination eliminated the galvanic corrosion that plagued scrap-based rebar. Engineers at the Ohio Bridge Project expressed amazement at the test results. They had grown accustomed to rebar from mini-mills that barely met 50,000-pound yield requirements, with elongation values around 5% that raised concerns about crack propagation under cyclic loading. The structural calculations for major infrastructure projects assumed these minimum values, building in safety factors to compensate for material limitations. Reynolds visited the bridge construction site during the summer of 1964, watching crews place his rebar in the massive concrete pours that would anchor the suspension cables. A construction foreman remarked that the bars felt different, somehow more substantial than typical rebar, with surface finish and dimensional consistency that made placement easier and more precise. The market was beginning to take notice, but not necessarily in ways that favored integrated mill production. Electric arc furnace operations were expanding rapidly, with new mini-mills announcing construction from Texas to Pennsylvania. The economics of scrap-based steelmaking continued to improve as electric power costs declined and scrap availability increased from urban demolition and automotive recycling. Standing beside the cooling bed where the latest production run lay gleaming in the Indiana sunlight, Reynolds allowed himself a moment of satisfaction. His rebar had proven its technical superiority in every measurable way. The question now was whether American infrastructure development would recognize the value of longevity over initial cost savings. The call came at 6:30 on a Tuesday morning in September 1967. A highway overpass under construction in Pennsylvania had experienced what the engineering report would diplomatically term structural failure during load testing. The rebar supplied by a mini-mill operation in Pittsburgh had failed to meet elongation specifications, achieving only 4% elongation instead of the required 8%. When test loads approached design capacity, several reinforcing bars had snapped with the brittle fracture characteristic of improperly processed steel. No one died in the partial collapse, but the liability implications sent shockwaves through the construction industry. The contractor faced $1.2 million in litigation costs, schedule delays that would extend the project completion by 8 months, and the expensive challenge of removing defective reinforcing steel from partially cured concrete. Insurance investigators descended on the mini-mill that had supplied the failed rebar, examining production records that revealed the cost-cutting measures Reynolds had long predicted would lead to disaster. The Pittsburgh mini-mill had been pushing production rates to maximize throughput, feeding high-copper automotive scrap into electric arc furnaces, and using rapid quench cooling to achieve yield strength specifications. The resulting microstructure contained brittle martensite phases and retained stresses that made the bars prone to sudden failure under loading. Elongation testing had been perfunctory, with samples cherry-picked from production runs rather than randomly selected from shipped material. Within weeks of the Pennsylvania failure, engineering firms across the Midwest were specifying integrated mill rebar from virgin iron sources for critical infrastructure projects. The Longspan Rebar Works received inquiries for bridge reinforcement contracts that would have represented the largest orders in the plant's history. Reynolds found himself in the ironic position of Vindication, arriving precisely when his operation was least prepared to capitalize on it. The troubles had begun in July when longshoremen struck the Great Lakes ore docks, halting shipments of taconite pellets from Minnesota's iron ranges. The work stoppage stretched for 12 weeks, forcing Reynolds to draw down inventory that had been carefully accumulated for steady production. By October, the blast furnaces were operating on emergency reserves, creating bottlenecks throughout the steel-making process that made consistent chemistry control increasingly difficult. The refractory failure struck in November with devastating timing. The No. 2 blast furnace developed cracks in its hearth lining during a routine campaign, allowing molten iron to contact the furnace shell and forcing an immediate shutdown. Refractory repair required 4 weeks of round-the-clock work, during which the plant's iron production dropped by 60%. The remaining blast furnaces, already strained by the ore shortage, could not maintain the pig iron supply that Reynolds's chemistry specifications demanded. Scrap markets compounded the crisis. Industrial demolition had slowed during the economic uncertainties of 1967, reducing the supply of high-grade structural steel that met Reynolds's stringent copper limits. Automotive scrap remained plentiful, but Reynolds refused to compromise his specifications by accepting material with unknown alloy content. The scrap he would accept had increased in price by 15%. While the market price for finished rebar remained stubbornly below $450 per ton, Edward Carmichael, the corporate production director, arrived in Gary during the first week of December with charts and graphs that painted the long-span rebar works as an economic anachronism. Many mills across the country were expanding capacity, driven by electric arc furnace technology that could produce rebar in hours rather than days. Their scrap-based feeding eliminated the complex logistics of iron ore mining, Great Lakes shipping, and blast furnace operations. Quench-and-temper techniques could boost yield strength to 70,000 pounds per square inch, creating marketing advantages that impressed procurement officers focused on specifications rather than long-term performance. Carmichael's presentation to the plant management team was methodical and compelling. The integrated mill approach required virgin iron ore at $65 per ton, basic oxygen converter processing that consumed expensive oxygen, and air cooling systems that tied up production capacity for extended periods. Many mills using electric arc furnaces could feed automotive scrap at $35 per ton, achieve faster melting cycles, and boost throughput with rapid cooling techniques. Reynolds countered with metallurgical arguments that fell on increasingly deaf ears. Quenching finished bars might achieve higher yield strength, but the resulting microstructure contained brittle martensite phases that reduced elongation and created susceptibility to stress corrosion cracking. High copper automotive scrap introduced galvanic corrosion risks that would manifest years or decades after installation. Rapid cooling rates created residual stresses and decarburized surface layers that compromised long-term durability. The financial results for calendar year 1968 made technical arguments irrelevant. The long-span rebar works recorded a loss of $2.1 million, the worst performance in the plant's 40-year history. Fixed costs associated with blast furnace operations, the extended reheating furnaces, and the specialized cooling beds could not be justified by production volumes that had fallen to 60% of capacity. The board meeting convened on a bitter January morning in 1969. Corporate executives presented closure options that would eliminate the rebar line entirely, converting the rolling mill to produce merchant bar steel for less demanding applications. Alternative proposals called for massive retooling to electric arc furnace operations, scrapping the blast furnaces, and converting to scrap-based feeding with rapid cooling systems. Maria Lopez had worked the long-span rebar work since she was 19 years old, learning the craft from men who had rolled steel during World War II. She had watched 3 generations of her family contribute to American infrastructure, taking pride in knowing that bridges and buildings across the Midwest contained steel that bore her personal attention to quality. The prospect of converting to mini-mill techniques represented more than operational change. It meant abandoning standards that connected her work to something larger than immediate profit margins. Standing before the assembled management team, Lopez spoke with quiet intensity about responsibility that transcended quarterly earnings reports. We learned from Dad and Granddad that good steel lives. If we cut corners now, I worry what happens when someone's kid crosses the bridge I built. Her words carried the weight of personal conviction, the knowledge that infrastructure decisions made in corporate conference rooms would affect real people for generations. The emotional appeal resonated, but economic reality remained implacable. The plant sat idle for 3 weeks while the board deliberated, blast furnaces banked but not extinguished, rolling mill equipment silent except for the maintenance crews who kept systems ready for whatever decision emerged from corporate headquarters. Reynolds walked the empty production floor during those uncertain weeks, past cooling beds that should have been filled with slowly cooling rebar, past reheating furnaces that consumed fuel without producing steel. The technical vindication he had sought, proof that integrated mill quality exceeded mini-mill economics, had arrived too late to save his operation. The Pennsylvania bridge failure had validated his predictions about scrap-based rebar, but validation without financial sustainability was merely expensive correctness. The irony was sharp and bitter.
American infrastructure needed rebar that would last 75 years
But American business demanded profits that materialized within 75 days. Reynolds spent the winter of 1969 developing what the board would either embrace as visionary engineering or reject as financial suicide. His recovery plan represented the complete opposite of industry trends, a deliberate rejection of every cost-cutting measure that had made mini mills competitive. Where other operations were increasing scrap content, Reynolds proposed eliminating scrap feed entirely for his premium line. Where competitors were shortening processing times, he proposed extending them. Where the market demanded cheaper materials, he proposed specifying the most expensive inputs available. The technical specifications read like a manifesto against commodity steel philosophy. The long-span rebar works would convert to exclusively virgin iron ore, sourced from Minnesota taconite operations with iron content above 63% and phosphorus levels below 0.02%. Scrap would be eliminated entirely from premium production runs, or limited to very high-grade structural steel with copper content below 0.05%. Material so pure it cost more than many finished steel products. The centerpiece of Reynolds's proposal was a $1.4 million investment in a new homogenizing furnace, a massive reheating system that would ensure complete chemistry uniformity throughout each billet before rolling. The furnace would operate at carefully controlled temperatures, using zone heating to eliminate the chemistry variations that could create weak spots in finished bars. Every billet would spend minimum 4 hours at 1250 degrees Fahrenheit, longer than any competitor considered economically justifiable. The cooling system modifications represented Reynolds's most radical departure from industry practice. Instead of the 45-foot run-out bed that had served the plant since the 1940s, he proposed extending cooling length to 60 feet, allowing finished bars to air-cool for a full hour rather than 45 minutes. The extended cooling time would ensure complete transformation to fine pearlite and ferrite microstructure, eliminating any possibility of bainite formation that could compromise long-term ductility. Reynolds also mandated concrete cover specifications that exceeded standard construction practice. Major infrastructure contracts would require 4½ inches of concrete cover over reinforcing bars, compared to the 3½ inch standard that most projects specified. The additional concrete would provide enhanced protection against environmental exposure, extending corrosion resistance by decades in marine or industrial environments. The board's decision came in March 1970, driven less by confidence in Reynolds's technical arguments than by the mounting evidence that mini-mill rebar was failing in service. Bridge inspection reports from across the Midwest were documenting premature corrosion in structures less than 10 years old, while liability costs from the Pennsylvania overpass failure had reached $3.8 million. Insurance companies were beginning to require proof of rebar quality for major infrastructure projects, creating market demand for premium materials that Reynolds was uniquely positioned to supply. The plant reopened in June 1970 with production protocols that would have impressed quality control engineers from the 1920s. Every heat of steel underwent spectroscopic analysis at multiple stages, from molten metal in the basic oxygen converter through final chemistry verification after casting. Carbon content was held between 4 3/10 and 4 5/10%, manganese at 7 9/10%, phosphorus below 2 5/10%, sulfur below 1 8/10%. The homogenizing furnace transformed billet quality in ways that exceeded Reynolds's projections. Chemistry uniformity improved by an order of magnitude, eliminating the composition variations that had occasionally created weak spots in finished bars. Microstructure became remarkably consistent, with grain size that remained uniform from bar surface to center. The extended heating cycle also eliminated internal stresses that could contribute to delayed cracking under service loads. Rolling operations incorporated refinements developed during the shutdown period. Billet reheating achieved more precise temperature control, with variation held within 10 degrees Fahrenheit throughout the billet length. The rolling mill passes were adjusted to minimize work hardening while maintaining the 12 ribs per foot that created superior bond with concrete. Surface finish improved dramatically, with dimensional tolerances that consistently achieved plus or minus 0.03 of an inch rather than the plus or minus 0.05 that had been considered acceptable. The extended cooling bed proved revolutionary in ways that surprised even Reynolds. Bar's cooling for 60 minutes developed microstructure so fine and uniform that mechanical properties exceeded specification requirements by substantial margins. Yield strength averaged 61,000 pounds per square inch, with remarkably low variation between bars. Elongation values consistently exceeded 10%, indicating ductility that would resist brittle failure under extreme loading conditions. The first major validation came in 1971 with a 45,000-ton order for the Glen Canyon Dam Reinforcement Project. The hydroelectric facility required rebar that would perform in concrete exposed to reservoir water for potentially centuries, demanding corrosion resistance that exceeded any previous infrastructure application. Construction specifications called for bars that would maintain structural integrity under massive hydrostatic loads while resisting chemical attack from mineralized water. Quality assurance testing documented performance that vindicated every aspect of Reynolds' technical approach. Tensile tests on random samples showed yield strength averaging 60,500 pounds per square inch, ultimate strength reaching 91,000 pounds per square inch, with elongation at fracture consistently above 10%. The microstructure revealed fine pearlite with ferrite islands, completely free of the temper embrittlement that plagued rapidly cooled bars. Corrosion testing provided the most dramatic confirmation of integrated mill superiority. Test coupons exposed to accelerated corrosion conditions for 2 years showed metal loss below 0.03 of a millimeter per year, projecting service life exceeding 75 years even in aggressive environments. The low sulfur and phosphorus content that Reynolds had insisted upon eliminated the inclusion sites where corrosion typically initiated, while the absence of copper contamination prevented galvanic corrosion that degraded scrap-based materials. Dr. Alan Grayson's metallurgical analysis confirmed the fundamental soundness of Reynolds' technical philosophy. "The microstructure is exactly what you want for long-term service," he reported after examining samples from the dam project. "Fine pearlite with ferrite islands, no carbide precipitation, no evidence of strain aging or temper embrittlement. This steel will outlast the concrete it reinforces." Meanwhile, mini-mill competition continued expanding capacity with rebar that met minimum specifications while sacrificing long-term durability. Electric arc furnace operations produced bars with 50,000-pound yield strength and 6% elongation, adequate for immediate construction needs but marginal for extended service life. Corrosion rates averaged 0.15 of a millimeter per year, projecting replacement requirements within 30 to 40 years for structures designed to last a century. The market was beginning to recognize the difference. State departments of transportation started specifying integrated mill rebar from virgin iron sources for critical bridge projects. Engineering firms working on major infrastructure developed internal specifications that effectively required Reynolds' production standards. The long-span rebar works became known throughout the construction industry as the source for legacy bars, reinforcing steel designed for generational durability. Orders flooded in from projects that demanded the highest quality materials. Nuclear power plant construction, major dam renovations, bridge replacements in marine environments, applications where failure was unacceptable, and service life measured in decades rather than years. The premium pricing that had seemed economically suicidal during the crisis now represented appropriate compensation for demonstrable technical superiority. Reynolds stood beside the extended cooling bed on a humid August evening in 1972, watching the latest production run of legacy bars cool slowly in the Indiana air. The plant was operating at capacity for the first time since 1966, with order backlogs extending 6 months into the future. The technical vindication he had sought was complete, validated not by academic theory, but by infrastructure performance that would endure for generations. The core drilling began at dawn on a crisp October morning in 2015. 51 years after the first pours of concrete had anchored the Ohio River Bridge to its bedrock foundations, a team of structural engineers was extracting cylindrical samples from the tower anchor reinforcement to determine whether the aging infrastructure could safely carry traffic loads for another generation. The bridge had served Interstate 71 faithfully since 1964, but federal inspection requirements mandated comprehensive evaluation of all structures approaching their sixth decade of service. Dr. Sarah Mitchell, the lead forensic engineer, had examined hundreds of aging concrete structures throughout her career, and she approached the Ohio Bridge inspection with the methodical skepticism that experience had taught her. Most reinforced concrete from the 1960s showed predictable signs of deterioration, surface spalling from freeze-thaw cycles, rust stains indicating corrosion of embedded steel, reduced load capacity as reinforcing bars gradually lost cross-sectional area to oxidation. The typical infrastructure built during America's post-war construction boom was approaching replacement time, requiring massive public investment to maintain safe transportation networks. The first surprise came when the core drilling equipment extracted concrete samples that showed remarkably little deterioration. The 4 1/2-inch concrete cover that Reynolds had specified in 1964 remained sound and dense, with minimal cracking and no evidence of the chloride penetration that typically preceded reinforcement corrosion. The concrete-steel interface showed excellent preservation of the alkaline environment that protected embedded rebar from oxidation. When the drilling finally reached the reinforcing bars themselves, the extracted samples revealed steel that looked remarkably fresh for its age. The 12 ribs per foot remained sharp and well-defined, with no evidence of the surface pitting that characterized corroded rebar. The deformation pattern showed no degradation of the mechanical bond that anchored these bars within their concrete matrix. Most remarkably, the bar surfaces showed only minimal rust scale formation, suggesting corrosion rates far below typical infrastructure steel. Laboratory testing of the extracted bars provided quantitative validation of their exceptional preservation. Tensile tests revealed yield strength between 57,000 and 59,000 pounds per square inch, essentially unchanged from the original 60,000 plus values documented in 1964. Ultimate strength remained above 85,000 pounds per square inch. Most significantly, elongation at fracture still measured 9%, indicating that the steel retained the ductility that prevented brittle failure under extreme loading. Dr. Alan Grayson, now in his 80s but still consulting on materials failures, examined the microstructure of the extracted samples under high magnification. The fine perlite and ferrite structure that Reynolds had achieved through careful air cooling remained intact after 5 decades of service. No evidence of strain aging, no carbide precipitation, no grain boundary embrittlement that typically degraded steel properties over time. The metallurgical integrity was remarkable for infrastructure steel of any age, unprecedented for reinforcement approaching 60 years in service. Corrosion rate measurements provided the most dramatic evidence of the integrated mill advantage. Careful analysis of metal loss indicated corrosion proceeding at less than 0.02 of a millimeter per year, a rate so slow that the bars would retain structural adequacy for well over a century. The low sulfur and phosphorus content that Reynolds had insisted upon had eliminated the inclusion sites where corrosion typically initiated, while the absence of copper contamination prevented the galvanic effects that accelerated degradation in scrap-based materials. The contrast became stark when the inspection team examined a commuter rail overpass less than 5 miles downstream, built in 1998 using conventional mini-mill rebar. Despite being 33 years newer than the interstate bridge, the rail structure showed extensive corrosion damage. Surface spalling exposed reinforcing bars that were heavily pitted, with visible reduction in cross-sectional area. Tensile testing of extracted samples revealed yield strength degraded to 47,000 pounds per square inch, elongation reduced to 5%, and corrosion rates averaging 0.12 of a millimeter per year. The engineering implications were profound. The 1998 overpass, built with state-of-the-art construction methods and materials that met contemporary specifications, showed projected remaining service life of less than 25 years before major rehabilitation would be required. The 1964 bridge, constructed with what the steel industry had dismissed as economically obsolete methods, retained structural integrity that would support traffic loads well into the 22nd century. Maria Lopez, now 74 and long retired from the long-span rebar works, attended the 50th anniversary reunion of the plant's premium rebar program on a warm September evening in 2014. The gathering brought together workers, engineers, and managers who had participated in Reynolds's controversial decision to pursue quality over cost during the transformation of American steelmaking. Many carried photographs of infrastructure projects they had helped build, bridges spanning major rivers, dam reinforcements that would contain reservoir water for centuries, building foundations that would support urban skylines for generations. Lopez walked slowly among the displays of core samples and metallurgical analysis that documented the exceptional performance of their legacy bars. She paused before a cross-section of rebar extracted from the Glen Canyon Dam, where steel they had rolled in 1971 continued to perform flawlessly after 4 decades underwater. The fine perlite microstructure remained clearly visible in the polished sample, testimony to the air cooling process she had supervised with such attention to detail. A younger engineer approached Lopez with questions about the original production methods. How had they achieved such consistent chemistry control? Why had air cooling produced superior microstructure to rapid quenching? What had convinced them to specify concrete cover thicknesses that seemed excessive by contemporary standards? Lopez answered patiently, drawing on memories of conversations with Jack Reynolds and Dr. Grayson about metallurgy principles that connected steel chemistry to infrastructure longevity. The conversation turned to the broader implications of their technical choices. American infrastructure built during the 1960s with integrated mill rebar was outlasting structures built decades later with materials that met higher strength specifications but sacrificed durability for cost reduction. The decision to resist commodity steel pressures, to maintain virgin iron sourcing, strict chemistry control, extended cooling times, and generous concrete protection had created infrastructure assets that would serve the nation for over a century. Lopez picked up a sample of the legacy bar that bore her shift markings from 1972, stroking the ribbed surface with fingers that remembered the texture of properly finished steel. The 12 ribs per foot remained sharp after 43 years in service, the 0.04 inch depth unchanged, the spacing precise. This was steel that had been made to last, crafted by workers who understood that infrastructure decisions made in mill towns would affect communities for generations. The Vindication was complete, but it carried sobering implications for American competitiveness. The engineering approach that created superior infrastructure, careful material sourcing, extended processing times, generous safety margins, premium pricing that reflected true lifetime value had been largely abandoned in favor of methods that optimized immediate cost reduction over long-term performance. The mini-mill revolution that had seemed inevitable during the 1960s had indeed transformed American steelmaking, but at the expense of durability that only became apparent decades later. Standing in the warm evening air outside the shuttered long-span rebar works, Lopez reflected on the paradox of American industrial innovation. They had built rebar in the 1960s that still outperformed materials produced with more advanced technology 50 years later, because quality-first engineering and disciplined materials science had proven more valuable than the cost-cutting efficiency that market forces demanded.